Hello everyone. I hope everyone is having an amazing day over there. I'm glad that you are able to join me again. So we are going to continue our discussion of AIATS plus phase 2 of the test, mock test 7 that was conducted on 2nd of March 2025. All right, and we are going to continue from where we left off last week, okay, with a different list of topics before us. So as you can see, thermal properties of matter, dual nature, EMI, and moving charges. So these three are from your 12th class, right? The ones I have crossed, and these two are from your 11th class. All right. So let's begin. I hope you will have a wonderful session today. All right. So first, we are going to start with thermal properties, and we are going to cover the questions that had come in your test, right, a couple of days back. So we begin with the topic Newton's law of cooling, right? This you are already familiar with, right? So let's say you have a body, right? Right, a body which has a temperature, let's say, more than the temperature of surroundings. All right. So what happens to that body? It will start cooling, isn't it? So let's say, for example, you have a hot cup of tea, right? You have kept it on your table. So what happens to that tea? It will start cooling, right? And eventually, what will happen? As the temperature drops, it will try to achieve which temperature? The temperature of surroundings, right? So for example, so let's say this is a ball or a body, right? Its temperature is, let's say, T, and we have the temperature of surroundings as, let's say, Ts. I'm denoting it as Ts, right? So Newton's law of cooling, it states that, please pay attention, that the rate of cooling of this body would be proportional to the change in temperature, right? Or we can, let's say, call it as temperature difference between the body and surroundings. Okay, body and surroundings. So let's begin with, first of all, you need to remember this expression, right? Minus dq by dt. So what is dq here? It is the, let's say, the loss of heat, right? Or let's say minus dq by dt, and we say it is proportional to the change in temperature or the temperature difference, right? So T minus T surrounding, right? This would be proportional. Now when we remove this constant of proportionality, we get a constant, right? That constant, let's say, we are calling it as K, or you can call it as C also if you want, K T minus Ts, okay? And then dq, as you already know, you have another formula for it as well, connected with the mass of the body, right? So let's say its mass is small m, and it has some specific heat as well. So specific heat of the body is, let's say, small s, right? So how much heat it is going to lose, that is also connected with the temperature of that body. By which formula? Right, by which formula? Let me write over here. So dq is, let's say, the heat exchange, right? Heat exchanged with surroundings. So dq would be written as ms dt, right? dt is the very, very small change in temperature of this body, right? So when we substitute this formula over here, isn't it? So we can substitute, see this dq, you can substitute over here, right? So what would you arrive at? Just put it. So minus ms dt by dt is equal to k times T minus Ts, right? So what are these things over here? M and S I already told you. dt, let me tell you again, dt is the change in temperature, okay? So minus dt, you can call it the fall in temperature of this body, right? Because the temperature T, it is going to decrease, isn't it? I told you at the beginning that temperature of body is going to fall. So T is going to decrease. The change in temperature will be negative, minus dt will be positive. Okay. So from here, from this whole exercise, we can conclude right? We can conclude that this minus dt by dt, right? It is proportional to T minus Ts, right? This is the result that we have obtained over here. Okay. So this we can call it as rate of cooling as well, right? The rate of cooling is proportional to the temperature difference between body and surroundings. All right. And in your NCERT as well, if you see the last solved example, right? That is the one which connects with the next problem that we are going to do. And it is the formula which we are going to use. Now let's see. Let's see the question. See over here. What are they saying? The temperature of a body is falling from, say, 80 to 50 degrees Celsius in 6 minutes. Okay. And they're asking the time it takes to cool from some other temperature to some other temperature. All right. So we are going to use this formula over here. But we are going to use a trick. We can call it like that. Right. See how? This dt minus dt, I can write it as change in temperature. Okay. This dt small, this one I can write it as time taken. And this is the temperature difference between body and surroundings. Okay. So if you want, I can conclude over here. All right. So change in temperature of body, right, upon time taken, right, is proportional to T minus Ts. T is what? T average. All right. T average, the average temperature of the body, minus temperature of surroundings. We are going to directly write over here. See how? What will be the change in temperature of the body? Or if you want, you can also call it the fall in temperature. So fall in temperature is how much? 30, right? So 30 degree fall in temperature upon time taken, degree. Time taken is how much? 6 minutes. And I had written proportional to over here. So proportional to means if you remove this proportionality, you will get another constant, right? So this we won't write it as k, you can write some other constant. Let's say k1 or c, for example. All right. So let's say that constant is c. Temperature change. So what is the average temperature of the body here? The average 80 plus 50 by 2. That is how much? 65. 65 minus temperature of surroundings, right? And surrounding temperature is 20. So you'll write 20 over here. Okay. Then let's write another equation as well, right? Because they are asking time it takes to cool from 60 to 40, right? So now what is the fall in temperature? 60 minus 40, that is 20 degree, right? Here also it is degrees only. And 20 degree upon time taken, we don't know. Let's call it as T. The constant is the same. Now here, the difference. What is the average temperature of the body? 60 plus 40 by 2. So that means 50 minus temperature of surrounding is 20. Okay, see, very simply we have employed that formula. So now you can directly find this small t, right? All you have to do is take their ratio, right? Because this would become 45C, isn't it? For now I am not writing that unit degrees, and this one is your 30C. So take the ratios, see what would become, 6 will go down, T will go at the top. So taking the ratios, 30 by 20 into T by 6 is equal to, take this ratio, 45 by 30. Okay. If you cancel the terms, 0, 0 get cancelled, and this one, you cancel it by 15, right? So 3 by 2, 3 by 2, 3 by 2, they will also get cancelled. So what remains is T by 6 is equal to 1, right? T by 6 is equal to 1, and obviously small t is in your minutes. Okay. So T would come out to be 6 minutes. Okay. T would come out to be 6 minutes. So this simple method you can employ to solve such questions. All right. We have, I will give you a homework as well. From the same topic, I will give you a homework before leaving. Very well. Okay. So now we're moving on to our next topic, dual nature, right? And the moment you hear the word dual nature, right, Einstein's photoelectric equation should pop up in your mind, right? And that is what we are going to discuss also. So let's say, right, we have a metal surface, right? We have a metal surface on which electromagnetic radiation is falling down, all right? And remember, this radiation, we say, is composed of packets, okay, packets of energy. And these packets are called quanta, right? Okay, called quanta, all right? So, and what would be the energy of one packet or the energy of one quanta? Right, so the energy of one such packet or one quanta, right, or we can also call it energy of one photon, right, because these packets, they are essentially photons only, all right. So energy of one photon, okay, not multiple photon, only one photon. So that can be expressed as h into nu, right. So if you see in this figure, so whatever this energy that is falling over here, right, this energy I am talking about, okay, this energy, this is falling in the form of packets or quanta or photons. So energy of one photon is h into nu, all right. And what is h over here? This you are already aware of. H is the Planck's constant and nu is your frequency, okay. And these values also you need to remember. They can be directly asked in your NEET exam as well, all right. Planck's constant, which is given by 6.626 into 10 raised to the power minus 34 joule second, all right. Sometimes we take the approximation 6.63 for solving the question. And what is nu over here? Nu is the frequency of incident light, which is falling in the form of quanta. Okay. So this much energy is falling on the metal surface. So what are these photons they are going to do when they fall on this metal surface, right? If you see, the metal surface is filled with electrons. So what are these packets or quanta going to do? They will try to knock out these electrons, right? And then what will happen? These electrons will be emitted from the surface, isn't it? They will be emitted. So we can write the photoelectric equation, right? So let's say energy of emitted electron, and also remember this photoelectric equation talks about the kinetic energy, or we can say the maximum kinetic energy of the ejected or emitted photoelectron, right? Because photoelectron can also be emitted with zero energy also. That is also possible. I'll explain. So this would be equal to, or we can also call it kinetic energy, all right. So kinetic energy, or we can also call it Ke max, because just now I told you it is the maximum kinetic energy, all right. And this would be equal to h nu, right, h nu minus, why minus? Because let's say if this much energy is falling on that metal surface, doesn't mean that the photoelectron that is ejected, it will have that same energy. That's not possible, right? It's going to lose some energy. Because of who? Because of who? Because of this one, what you got over here, right? What is this? The metal plate, right? So because of metal plate, the photoelectron, you can say, is losing some energy. And that one is called phi. Phi is nothing but work function. This depends on the metal surface. Please remember, phi does not depend on the incident light, and h nu depends on your incident light, and this one, it belongs to your photoelectron, okay. Or if you want, you can also write down maximum energy, all right, or we can write maximum kinetic energy also, kinetic energy, all right. So let me write the same formula over here. So K max or Ke max is equal to h nu minus work function, All right. So this photoelectron is now ejected. Now what happens? We can apply some potential across the electrodes to stop this photoelectron, right? So how much, which photoelectron I'm talking about? The photoelectron which is being ejected with this much energy, K max. So for that one, how much stopping potential we have to deploy? That potential is called stopping potential, all right? So that potential, so let me write over here. Potential, okay, to stop this photoelectron is equal to, let's say, I'm calling it Vs, S for stopping potential, all right. So what will be the energy? How much energy you are supplying? Charge into potential, isn't it? You have studied work done is equal to charge into potential, energy is equal to charge into potential. Charge means, what is the charge on photoelectron? E only, isn't it? Let me also write that down. Charge on electron is, let's say, E. So how much is the energy you are providing? E into Vs, right? And obviously charge will be negative, okay, minus 1.6 into 10 raised to minus 19 coulomb. So how much would be the energy? E into Vs, and that much energy has to be equal to K max, isn't it? So let's say, for example, let's say K max is coming as 12 joule, which is not possible, remember, because we're talking about electron, right? So let's say it is 12 joule, for example. So how much energy, or we can say how much minimum energy you have to provide to stop that photoelectron completely? 12 joule only, right? But in the opposite direction, obviously, right? So which is why, like just like over there, this potential, we say that it is the minimum potential that needs to be deployed, all right? So this, please remember, this is the minimum potential, all right? So let me write over here so that you guys can remember minimum, or let me write like this, minimum, all right? The minimum potential, that is your stopping potential, all right? So please remember, this is stopping potential. All right. So what does the formula become now? Right, the formula becomes K max has to be equal to E into Vs. That's what I explained just now, right? E into Vs is equal to this thing. All right. So let's do a question. I hope you are able to understand. If you understand this much, see over here. I was talking about photons. So photon of energy. This energy is given, right? Now this is what? This is your h into nu, right? Photon of energy 5 electron volt are incident on a surface of work function 2.4 electron volt. Work function, right? So work function I had denoted by the symbol phi. Okay. The magnitude of stopping potential, they are asking the magnitude, right? So first let's find K max. K max, write the formula. It is h nu minus phi. H nu is how much? 5 electron volt, right? Minus phi is what? Work function, which is work function is due to the metal surface, and that is how much? 2.4, and this comes out as how much? 2.6, and what would be the unit? Electron volt, right? So 2.6 electron volt. It is the maximum energy or maximum kinetic energy of ejected photoelectron, right? So corresponding to that, you have to provide how much stopping potential? 2.6 volt, but in the opposite sense, I had told you, right? So stopping potential, just now I told you, it was, you can also call it the maximum or the minimum negative potential, right? Because negative, why? Because we are applying it in the opposite direction. We want to stop that photoelectron from moving, okay? But here they are only talking about the magnitude. So please don't get confused, right? The magnitude. So this is the energy, and if you want to get the potential, what you have to do? Just simply equate it to E into Vs, okay? This E and E will get cancelled, and you are left with the stopping potential or its magnitude, all right? So stopping potential becomes 2.6 volt, okay? So please see over here, all right? Yeah. Yeah, good afternoon, Lakshman. A very good afternoon to you. Okay. All right. So let's do this question as well. Pretty much the same question, right, as the last one, but they're asking something else. Here they're asking maximum kinetic energy. The maximum kinetic energy of ejected photoelectrons, right? And this we have already done just now, isn't it? How much it was? 2.6 electron volt. Okay. All right. So moving on to our next topic, electromagnetic induction, right? You have already discussed in this topic Faraday's two laws that you need to remember by heart. Okay, I will also show you what the laws are. But under this one, we are going to especially talk about another law. Okay, another law, which is your Lenz law. Okay, which is your Lenz law. So what does that state? So first, before moving on to Lenz law, first talk about Faraday's two laws, right? Faraday's first law and second law. So what were they exactly? That, let's say, for example, you have a circular loop, right? And magnetic field lines are going through that loop, right? So what will happen? Let's say you are increasing the number of magnetic field lines. So if you are increasing, or let's say decreasing, the flux is going to change. Flux meaning phi. You have to remember these symbols as well. So flux is going to change. Now flux changes with time, EMF will be generated. So this is what Faraday was talking about. All right. And the sign of polarity of that EMF, that we would be finding using Lenz law. The sign, remember. But the formulas are contained in Faraday's first law and second law. So let's see with an example. And we will also be talking about some diagrams which are given in your NCERT, right? So it will be interesting. Okay, see over here. Faraday's first law, right? Please read the statement, right? States that a changing magnetic field induces an electromotive force in a nearby conductor. Just now I told you, right? If you change the magnetic field, you change the magnetic flux and you induce an electromotive force, which is EMF in short. EMF in a nearby conductor. Okay. And Faraday's second law had given you the formula for it. First law was just a simple statement, right? So second law, if you see, it details until now we have not reached Lenz law, by the way. All right. So second law states that magnitude of EMF is directly proportional to the rate of change of magnetic flux through the circuit, right? Proportional to, or we can remove the proportionality and we get EMF that is induced is equal to minus d phi by dt. All right. So for example, let's say you have a loop like this, right? And you have a magnet with let's say north pole and south pole like this, right? And you have kept it stationary with respect to this loop, right? And remember, this is a conductor implying that current can flow, right? And you are not moving this magnet. So now can you tell me, will EMF be induced in here, in this one? No, right? No. Why no? Because Faraday's second law said EMF induced is equal to minus d phi by dt. So for d phi by dt, you need a changing flux. So for a changing flux, you need different number of magnetic field lines to penetrate this cross section, right? So if I draw the cross section, this is the cross section of that conductor, right? So the flux has to change through this loop. Okay, so only then EMF will be induced. All right, so let me again repeat it. So phi needs to change with respect to time. So only then EMF will be induced. And what is phi, by the way? Phi is your flux, which is given by, these topics also you have covered already. So flux is given by B dot A, right? Composed of two components, magnetic field and area vector. All right. So coming to Lenz law. So what does Lenz law say? That when EMF is induced, right? So for example, you have this magnet which is approaching this coil, right? You have a magnet which is approaching this coil, or if you want, I can show it with a bigger diagram, right over here. If you see, this magnet is approaching the coil, and there was, if you see, there is no battery connected over here, right? So there is no battery, and obviously it is a conductor, which means current can flow in this one, right? How is current induced in this one? as per Faraday's law, right? But how do we find the direction of that current? We use Lenz law for this one, all right? So please see carefully. So when this magnet is approaching, fast approaching, right? North pole is approaching. So the number of magnetic field lines which are going to come out from this north pole and enter this circular loop, it is going to increase, right? As it comes closer and closer. You can see over here, let me slide a little bit. So number of magnetic field lines is going to increase through this loop, right? So what does Lenz law say? That it is going to oppose this change in magnetic flux, right? Because magnetic flux is increasing through this loop. So Lenz law says it will try to oppose it. It will try to oppose it. So in order to oppose, this side of this coil has to behave as which pole, right? Because remember, current carrying coil can also behave like a magnet, all right? So this coil or this side of the coil will behave as, let me write down, north pole, all right? North pole meaning when north pole is approaching, this side will try to repel this magnet. So in order for repelling, this side should become the north pole. So north pole and north pole, they will repel each other, and in order to repel or in order to become a north pole, this coil has to induce a current through it, right? So let's say this was the coil, right? So if this becomes a north pole, which means it is going to get its own magnetic field lines and they are going to oppose this one. So they are entering, so through this coil or due to this coil, magnetic field, it will try to generate in the opposite direction, right? In opposite direction, that means you can use your right hand thumb rule, right, to find out the direction of induced current. All right, let me explain with another diagram as well. So if you see over here, the same diagram, just a different question, that's all. See, if the north pole is approaching, the current is induced in this manner, right? Why? Because it wants to oppose, all right? So we can again say north pole is approaching means the top side will behave as the north pole and the bottom side will behave as the south pole, all right? So in order to oppose, this top side becomes like a north pole and it will try to generate magnetic field lines in this direction in order to oppose the magnetic field lines due to this magnet, all right? So the current has to be like this, see? So that magnetic field lines go through the coil in this way, right? That is why, okay? So I hope you have understood. That's what I was talking about over there. So for this one, we can also draw the current as well, right? See, current, it will be like this. It is difficult to picturize using this diagram, but I hope this diagram is clear, right? You see, like this, okay? So it will try to oppose. It will try to produce its own magnetic field line in the opposite direction and oppose it. So this is what Lenz law was talking about, all right? And let's come back to here. And what was Faraday's second law? Faraday's second law said induced EMF, right? Lenz law is very less theory and more practical applications, okay? Even in your NCERT, if you see in your exercise the first problem, that's completely based on your Lenz law, all right? So induced EMF, this we have already studied, it is minus d phi by dt, right? And if it is a conductor, it has a resistance, and EMF by resistance will give you induced current, right? So induced current, let me give the symbol epsilon, and induced current, I'm calling it as I. I is equal to epsilon upon the resistance of that conductor, right? Simple current electricity formula, this one, right? And you can just substitute the formula over here, and I you can write by another thing. I you can also write it down as dq by dt, isn't it? This you again studied in current electricity chapter. I is dq by dt, where q is the charge flowing through the conductor. Epsilon, substitute over here, so that becomes 1 by r minus d phi by dt, okay? 1 by r minus d phi by dt, and if you want you can cancel, right? dt and dt you can cancel, right? So dq you are getting as how much? dq you are getting it as 1 by r minus d phi. All right. Now you can integrate both sides. If you integrate, what happens? See, we do integration like this. Okay. And I'm only asking you the induced charge in that conductor. You can find the induced current, you can find the induced charge. And induced charge, I'm only asking about the magnitude. Okay, not plus or minus. All right. Remember, this minus sign indicates the direction of that induced EMF or the induced current as per Lenz law. All right. So dq, this will become delta q, that is the induced charge. All right. So let me write down. This is your induced charge equal to 1 by r is your constant resistance of conductor. It won't change. It comes out of the integral sign, and integral minus d phi. That will become minus phi, right? And minus, as I said, it only denotes the direction. Okay. So for now, I am taking mod. I can take mod both sides. So this will become delta phi with a mod. All right. Mod meaning delta phi can also be positive or negative. So in order to remove that negative sign, I have put a mod over there. So very simple formula, right? Change in flux upon resistance gives you induced charge through the conductor or through the wire. All right. So using this much, we can solve, let's see what our next question is. And yeah, again, this one also, see, this we did not talk about. I think you can tell me. So I hope your concept is clear. You can tell me, right? North pole is not approaching now. It is going away, right? So which means the top side has to behave as what? Top side will try to oppose the change, right? So magnetic flux, which we saw over here, through this wire, magnetic flux was increasing. So it tried to oppose it. So in order to oppose, the top side became north pole. But here if you see, the magnetic flux is decreasing. Why decreasing? Because this is going away. It is receding, right? So if it is going away, this loop will try to pull it down or attract it. Attract it meaning this will try to behave as the south pole, right? The top side. All right. And the bottom one will behave as the north pole. Okay. North pole is the bottom one. That means magnetic field, it will try to produce magnetic field in the downward direction. So for that one, how should the current be induced, right? Current has to flow like this. See, current flow like this. So magnetic field is induced in the bottom direction. So bottom side is north pole and top side is south pole. All right, very well. See this one, Lenz law is based on what? It will be based on conservation of energy. All right, this is a pretty basic theoretical question this one was, because remember there should be no loss of energy, right? There is no external agent that is there which is trying to do some work or anything, right? You only had over here a coil and a magnet, right? So there should be no loss of energy. All right. So Lenz law makes sure of it, which is why we say that there will be conservation of energy. All right. There has to be conservation of energy. And also remember, Lenz law is, it tries to oppose the change in magnetic flux through that coil. So if magnetic flux is increasing, it will try to decrease. And if magnetic flux is decreasing, it will try to induce current so that it increases. Okay, so it will try to increase the magnetic field through it. Induced current will be such. All right, let's see. Now let's see another question over here. Yeah, Abhishek Singh is saying, oppose the cause of its production. Exactly. It will try to oppose or change, oppose the change. Okay, so let's see over here. Let's do another question. You have a coil of resistance 10 ohm. So this becomes R. R is your 10 ohm. Variation of current with time has been shown, right? Current with time has been shown. Time is in seconds, and this is 0.1. Okay, this is 0.1 seconds, and this is what? 4, meaning 4 ampere. All right. The magnitude of change in magnetic flux. They are asking change in magnetic flux, delta phi, isn't it? And they are asking the magnitude. This is what they are asking, isn't it? We did just now delta phi, and what did we do? We had written the formula. Delta Q is equal to delta phi by R, isn't it? So this is what they are asking. Resistance is already given. So this we have to find out. What is this? This is the induced charge or the charge that is flowing through the conductor, right? Or we can say in this case a coil, right? And how much is the charge flowing? At how much time we are supposed to find? See, the variation has been shown from 0 to 0.1 second. Alright, so this entire time interval has to be taken into consideration and we are going to find the charge. So how will we find the charge? Delta Q, it will be nothing but area under IT graph. Okay. Why area? Because remember, in current electricity chapter you have studied current is charge flowing through a cross section per unit time, right? So Q, charge flowing per unit time, so divided by time T. So I is equal to Q by T. Q will be what? I into T. Or if you see over here, I is changing as time is changing. So I into T meaning we will do area. I into T, area under the IT curve. And here what is the area? Area of triangle, isn't it? We have a beautiful triangle, we have to find the area. Half into base into height. What is the base? 0.1. Height is how much? 4. Half into 0.1 into 4, right? 2 multiplied by 0.1 is 0.2. So 0.2 what? Coulomb. SI unit of charge is coulomb. Now you substitute it over here, right? Put this one over here now. What becomes mod delta phi? Mod delta phi is Q, delta Q is how much? 0.2 coulomb, okay? So 0.2 multiplied by resistance is how much? 10 ohm, right? So I hope this one was clear, all right? From Faraday's law and from Lenz law, we are using this formula, all right? So please remember how we got this formula as well. So anyway, so 0.2 to 10 becomes 2, right? So 2 Weber, and Weber also remember is the unit of your flux, right? Or magnetic flux as we can call it. Even change in magnetic flux, obviously it will also have the same unit, Weber, all right? All right, so moving on to our next question. This is also interesting, right? See over here we have a question where inductors are given, right? And inductors with, what is that thing written over there? That is your inductance, right? Inductance, and in inductance, which inductance is it? Self-inductance or mutual inductance? It is self-inductance, all right? Self-inductance belongs exclusively to that inductor itself. Well, mutual inductance is due to two inductors, right? Their connection between them, their interaction between them leads to mutual inductance, all right? So here obviously they're asking equivalent inductance. They're talking about self-inductance only, all right? So if this is, let's say, L1, this is L2, and this is, let's say, L3, all right? Self-inductance, all right? So let me also write it down as well for you guys. Self-inductance, okay? And this question is a very, very simple question, right? You have to solve it just like the current electricity chapter, where if resistors were connected like this, and between P and Q, they're asking the equivalent resistance. So just like that, you have to solve this question also. And what happens when resistors are connected in parallel, right? Which formula we will use? 1 by R equivalent is equal to 1 by R1 plus 1 by R2, right? Or if the resistors are equal, having same resistance, R and R. So what will be the equivalent resistance? Two resistors are connected. Equivalent resistance will be R by 2, right? So if I am writing L equivalent over here, right? L1 and L2 in parallel, all right? L1 and L2 in parallel, which means due to these the equivalent would be L1 L2 upon L1 plus L2, right? How did we get this one? 1 by L parallel is equal to 1 by L1 plus 1 by L2. So if you solve it, take the LCM, you solve it, you will get this one, okay? This is for your LP. Or if you can directly remember, if the resistors are same, okay, let's say you have 3 resistors, 2 ohm, 2 ohm and 2 ohm. So what is the equivalent? Simple R by N. So 2 by 3, you have 3 resistors, right? Here only 2 are there, so 2 by 2. So 2 by 2 is how much? 1. So it is 1 Henry due to these, and now this much inductor and this inductor, they are in series. So in series combination, what happens if they are in series, right? So if L1 and L2 in series, then what will be the equivalent series resistance? It would be simple addition, all right? Just like in resistance, R1 plus R2. So here over here, we had 1 Henry, then plus 3 Henry. That's it. 4 is the answer, all right? Okay, 4. And this are all from your current electricity chapter. You can remember it like that, right? You can just please remember the final expressions, okay? But please remember, here we have not taken mutual inductance into consideration, all right? Because what does mutual inductor meaning? Meaning, when this inductor starts interacting with that one, all right? That means, see, remember this inductor, obviously there is going to be some magnetic field lines going through that one. What happens if this magnetic field lines, let me draw for you guys, although it's not required for this question, okay? So magnetic field lines which are going through this inductor, right? If they start interacting with this one, which means they pass through this inductor, this magnetic field line going through that inductor, or magnetic field line of that inductor going through this inductor, which means they are interacting, then mutual inductance will come into play. But here obviously we are neglecting, all right? So if you want, I can write that one also. So M is equal to, okay, so this one is not required, all right? M is equal to mutual inductance. We can just simply say ignored. So it is not taken into account. If it were taken into account, these things will change. Okay? All right. So very well. That was a very simple question, right? If you know how to find equivalent in resistors, you would be able to solve that question. All right. We are going to our next topic, center of mass, right? This also you have done a few questions already last week, right? So for example, if you have, let's say, disconnected bodies lying one over there, one over here, right? So what we do, so let's say you have this body M1, right? Then you have multiple bodies like that, okay? Okay, M1, M2, M3 and so on, M4, M5, M6, right? We can assume this whole system to be concentrated at its center of mass. That is why center of mass comes into play. Okay, we can assume that the entire mass, or let's say over here I have drawn 3 masses, right? So what will be M, that is mass of system. Mass of system, here it will be simply M1 plus M2 plus M3 and so on if it were more masses. So this total mass is capital M. We assume that the total mass is concentrated at its center of mass. Okay. So for example, let's say center of mass is somewhere over here, lying in between them. Okay. These 3 have some coordinates, x1, x2, x3, whatever. The center of mass will also have some coordinates. Okay. We can define the x coordinate of that center of mass. We can define the y coordinate and the z coordinate. Okay. This is also a simple formula which is given in your NCERT. So please remember. Yeah, Patrick Balco is asking why intensive batch is so late. Don't worry, you will be notified from your branch itself. So that is nothing to worry, right? All right, so coming back, for XCM, what will be the simple formula? See over here, multiply M1 with the x coordinate of M1, that is x1, right? Plus multiply M2 with x coordinate of M2, plus then again simply M3, x3 and so on. Okay, whole divided by capital M. Capital M is the total mass of the system. You repeat the same thing for YCM and ZCM also. The repeat exact same formula, right? YCM would become M1 Y1 plus M2 Y2 so on by capital M. Okay, in both these cases it will be division by capital M. Here also M1 Z1 so on. Okay, so M1 Z1 plus this one would be m1 y1 plus m2 y2 and so on. All right? And just as I told you, we are assuming that the whole mass is concentrated at center of mass. So let's do a question, a very simple question. Right? We have two bodies, m1, m2 is given, and their x coordinates are also given. Right? Very simple calculation. You see, this is the m1, this is the m2. Deploy that formula, x1, comma y1. Right? This is x2, comma y2. Right? Coordinates of center of mass they are asking. Center of mass cm, or sometimes we also denote it by com also. All right. So what will be x coordinate of cm? Use the formula m1 x1, right? m1 x1. So 1 into 1 plus m1 or m2 x2, right? If you want, I can draw arrows like this, right? m1 x1, then m2 x2. Here students generally commit the mistake, simple multiplication, right? So 2 into minus 1 upon total mass is how much? 1 plus 2, 3 kg. So divided by 3. Just have to solve it. See what 1 minus 2, minus 1 by 3. Very simple calculation. Similarly over here, YCM you can find out. M1, Y1. So 1 into 2, right? Plus 2 into 3. 2 into 3, right? M2, Y2, whole divided by total mass is 3. So what does this become? 2 plus 6, 8 by 3, all right? And remember, they are written in corresponding units, so SI units, whatever. So now, can you tell me what is the answer? Minus 1 by 3, comma, 8 by 3, which option? Third option. See, third option. Pretty simple, right? That one was. And remember, this representation or this whole plane or this whole body system was arranged in the xy plane, right? Because mass m1, m2, they are placed with xy coordinates, all right? Now what happens if that is not the case? Let's see the next question, right? Now see this question. The same thing I'm asking, find the coordinate of center of mass of this system. You have 3 masses, they are arranged as shown, right? There, if you see at the center, we have drawn a black dot and I have written some coordinates. Why? Why have I drawn this black dot? Because remember, what is this body? It's a solid sphere. A sphere cannot be contained in one plane, right? XY plane. So that means this system is arranged in 3D, right? But we can simply use 2D formula to solve this question. How? See, this whole system or this whole body, it is, we say, concentrated at 0, a, right, which is at its center. Okay, it is concentrated at its center. So this becomes your M1. Similarly, this one is concentrated over here, M2. This is concentrated over here. So M3, simple formula, right? So let's do XCM quickly. So what will be XCM? You can do it with me. If you want, you can pause the video and solve it and check it for yourself. M into x1. x1 is 0. 0. Then m into x2. Again 0. M into 0 is 0. Then m into x3 is a. So m into a is how much? ma. Whole divided by total mass of the system. So what is the total mass? m1, m2, m3. m plus m plus m. 3m. Right? 3m. So how much you are getting as the answer? M and m cancel. This you are getting it as a by 3. A by 3. And similarly, you can do solve for YCM also. You check for YCM. Please check. I'll leave this question as it is over here. But you please check. The answer will come to be option 3. Similarly, YCM also you will get as a by 3. Alright. So please do this portion. You can take this one as a very, very small homework. Alright. You can try it out. You will also get a by 3 again. Alright. So moving on to our last topic of the day. Last topic of today, moving charges and magnetism. It's a very, very interesting chapter in your 12th class, right? And here, we're just going to be discussing some formula and some very simple questions using that formula. Very simple, see? at the center of a circular loop. So for this one, please remember the formula due to arc. Okay, so let's say this is an arc, right, and at center O, right, and remember the arc has a radius, capital R, current is flowing, right, let's say current is flowing like this. You can flow current however you want, right, current I is flowing. So what will be magnetic field at the center of this arc? Let's say angle is theta. So please remember that formula, magnetic field at center, O will be equal to, right, mu naught I by 4 pi R into theta, right, into theta. If you remember this formula, you will be able to find this one for circular loop, right. So for circular loop, it's a circle obviously, right, and under this topic also I will give you a homework. Current I is flowing, right, radius is again R. So what will be the magnetic field at O? And remember, magnetic field is a vector, right? Here we have already drawn or written the magnitude. What is the vector or the direction? Remember, current is flowing like this, right? So curl your fingers along the current, thumb points in the direction of magnetic field, right? So magnetic field is into the plane, all right? Into the plane. Same over there as well. Or let's see, it might be different. If you curl your fingers, it is out of the plane. So here it is out of the plane, all right? But we have to deploy the same formula. The circle can be considered as an arc subtending how much angle? At the center, theta will become how much? 360 degree. That means 2 pi. So put 2 pi over here, mu naught I by 4 pi R into 2 pi. 2 and 4, they will get cancelled. Let me write it and show you. This way you will remember, mu naught I by 4 pi R into 2 pi, right? So this becomes pi get cancelled, pi cancelled, 2 and 4 also get cancelled, right? So how much you are getting? Mu naught I by 2R, all right? And also remember, this is not the derivation of this formula. We don't derive using this method, we remember using this method. So this is just a short trick for you to remember, all right? So mu naught I by 2R for circle. What about straight conductor? This also you have done in the previous few weeks, right? You have done many good questions also. Let me just recapitulate, right? So let's say you have a conductor, a straight current carrying conductor carrying current I, and at d distance away, let's say at this point O, you want to find the magnetic field, right? And let's say it is subtending at this O two separate angles, right? So let's say this angle is your alpha and this angle is your beta. So magnetic field at O, again use the same hand to find magnetic field direction at O, right? Place or point your thumb along the direction of current, curl your fingers like this. So magnetic field is going to be into the plane at O, okay? So B is equal to, whatever the value be, it will be into the plane, right? I think I am correct. And what will be the formula for that one? Very simple to remember, right? Mu naught I by 4 pi D. Okay, 4 pi D, just like we wrote over there 4 pi R, right? You see over here, we have written 4 pi R, mu naught I by 4 pi R. Here you can remember mu naught I by 4 pi D multiplied by sine alpha plus sine beta. Sine alpha plus sine beta. Alright. You can remember like this. I will give a question for straight current carrying conductor also. But that conductor formula did not come in your just concluded exam. Isn't it? What came in your exam was a very simple question. Two circular loops are given. So different radius obviously, R1 and R2. R2 is 4R. They carry currents I and 4I. And they are asking the ratio of magnetic field, right? So let's say this is your R1, okay? This is R1, this is R2. Current carrying, this is I1, this is I2, right? They are asking ratio of magnetic field. So first let's write magnetic field number 1 for circular loop. What was the formula? Mu naught I by, right? Mu naught I1 is I only by 2 R1. R1 is your R only. Okay, now for the second one, again mu naught I which one? I2, mu naught I2 by 2 R2, right? If you want I can write like this, 2 R2. Substitute the values. So mu naught I2 is 4I. So 4I by 2 into R2. R2 is how much? It is 4R, isn't it? R2 is 4R. So if you see over here, terms get cancelled, right? So what comes out is mu naught I by 2R only. The very same one, right? So B1 is equal to B2. That means the required ratio would be 1:1, right? You can write the expression if you know the formula. See, it was a very simple question, right? And this question, right? This question, if you want, you can take as an homework. All right? Let me just explain very simply. What are they saying? Let me read out for you guys. All right? The ratio of magnetic field here also you are supposed to find at the center of a current carrying circular wire. Current carrying circular wire and the magnetic field at the center of a square coil. A square coil, right? So first one is your circular wire and second one is a square. Okay, they are carrying current I, right? I believe the same current, and they are saying it is made from the same length of wire. So the length is remaining the same. So if I see over here, if let's say radius is R and here let's say side length is A, right? What will be the length of wire over here? Circumference 2 pi R, that is equal to length. And here what will be the length? The perimeter? Perimeter is 4A, that will be equal to length of wire, right? And this length is same. That means 2 pi R is connected to 4A. So that is first equation. All right. Now what are they asking? They are asking, see, ratio of magnetic field. So you have to write the expression for magnetic field, right? Isn't it? For this one you already know magnetic field expression at the center of coil, right? Which is what exactly? Mu naught I by 2R. Okay, so please write one over here. What about magnetic field over here at center O? And let's say, let me pass the current as well. Same current is flowing through them. All right. So I have explained the question. And also remember this one part of this square, right? Or let's say call it as one conductor, which means conductor, one conductor, means this conductor I am talking about. Okay, it has how much length? A. It is placed how much distance from the center? A by 2, isn't it? Because this whole length is A, this would be A by 2, right? So you can find, due to one wire you can find, right? We can find from 4 wires. So what will be magnetic field due to 4 wires? They are going to add up. Why add up? See, due to this wire, magnetic field going to be into the plane. Then due to this wire, the current is going flow over here. Due to that wire also, magnetic field is going to be into the plane. So magnetic field due to all 4 wires are going to add each other. And that magnetic field due to each wire is going to be equal also. So you can simply write magnetic field due to 4 wires. You can say it is 4 times magnetic field due to 1 wire. Right? And what was magnetic field due to 1 wire? That formula that we had written, right? Mu naught I by 4 pi d sine alpha plus sine beta. Now what is d over here? D is your A by 2. All right. Okay, so this becomes your d. Let me write d also, and alpha and beta also. This is your alpha, and this is your beta. Remember, this is a square, right? So it's going to be symmetric. So 45 degree, 45 degree. So magnetic field due to 1 wire, mu naught I by 4 pi d sine 45 degree plus 45 degree. Put this value over here, you will get this one. And what you have to do? Find the ratio. And this becomes what? Magnetic field due to square, right? And finally you have to do magnetic field due to circle by square, isn't it? Yeah, first circle is written. So magnetic field due to circle by magnetic field due to square. All right. This you have to find out. All right. And if you solve, you will get this one as the answer. All right. You can check it out for you guys. You can check it out yourself. All right, so we're coming the last topic of the day as well, under the last chapter, which is solenoid, right? Solenoid is, a general diagram is like this one, okay, which you must have seen in the market also, and in your NCERT, a rough diagram is also given. Okay, a long solenoid is what we are talking about. A long solenoid implies, if you want, I can write over here. Okay, a long solenoid. All right, and that means, firstly, magnetic field will be uniform. Magnetic field will be uniform in the interior of the solenoid. Everywhere magnetic field is going to have the same value, not just at the center or A, okay. That magnetic field will be equal to mu naught N into I. I is the current, N is the number of turns per unit length, and mu naught is, you already know, a constant, right? And another thing, remember that the length of the solenoid, okay. So the length of the solenoid is much greater than diameter of the solenoid. All right. Even in that case, we say it is a long solenoid. Okay. So let's say, for example, you have a question, right? You have a question. A long solenoid, number of turns per unit length is given. This becomes your N. Current is given. This becomes your I. And magnetic field, they are asking inside the solenoid. Simple formula you have to use, right? So B inside, this will become mu naught N I. So mu naught is what? Constant that has the value 4 pi into 10 power minus 7. N is how much? 1000. And I is how much? 1 by 4 pi. Okay, 1 by 4 pi. You can just cancel the terms. Right, 1000 into 10 power minus 7 becomes 10 power minus 4 Tesla. Right, Tesla is the SI unit of magnetic field. Or here, if you see, Weber per meter square is also given. And Weber we just now talked about, right? It is unit of flux. So flux per unit area is your magnetic field. In that way also unit has been expressed. You can simply write Tesla also. But either way, the answer will remain the same. 10 power minus 4. All right. Yeah, and this was, you can take it as another homework. Okay, here, you can, if you want, you can take a screenshot of that question. And the answer to this one would be 1:4. All right, 1:4. So I believe I have given 2 questions, right, as your homework. And if you see, let me come to the beginning of our presentation, right. There was another question that also you can take as your homework, right, because we have solved a similar question, right. Yeah, this question, right, which was the first topic we did today. Is it Newton's law of cooling? We did this question, if you remember, 80 to 50 in 6 minutes. Find the temperature after next 6 minutes. That is your homework, right? And for this one also, let me tell you the answer. It will come out as 35 degrees Celsius. All right, guys. So I guess we are done for today, and I hope you guys had a great time. So please keep revising, and thank you for watching the video.